Okay, we've laid out much of the beginnings or foundation for thermodynamics. We're going to take a little bit of a break now and talk about how matter looks and how it interacts, how molecules interact with each other on the microscopic scale. There's two motivations for this. The first one is that the primary way in which thermodynamic properties are predicted or looked into these days for complex molecular systems like proteins and DNA and the like is by molecular simulations, and molecular simulations use the kind of intermolecular interactions that we're going to talk about. So in talking about the interactions, we're going to take a step at least towards understanding those simulations. I suspect most people in the class have never encountered a simulation, but it's increasingly likely as time goes on that you will in later life. Let me say something a little bit, I guess, about simulations. This picture here is a little bit about how they work. You know, on the computer, there's a box designated. And that inside the box, there are a bunch of atoms placed, and placed means that their coordinates are stored on the computer, so their positions and their velocities. And then they're bonded to each other, so water molecule, the two hydrogens are bonded to each other. And then forces are calculated between the atoms, so between two bonded atoms, for example, between this oxygen and this carbon here, forces due to the bond are calculated, but also even when the molecules are far apart and not bonded to each other, there are through space interactions so that this oxygen atom will exert a force on this one over here and vice versa. So there's the force on this oxygen atom due to this oxygen atom over here, and there's the force, that green arrow, on this oxygen atom here due to this one over here. And using those forces, you can use Newton's equations, the laws of classical mechanics, to calculate accelerations, which then give the motions for each of the atoms in the system. And you do that in very small time steps, 10 to the minus 15 seconds, 1 femtosecond. And you just do it over and over and over and over and over again. Once you've got the program going, it's absolutely boring. The program just churns along, calculating tiny little moves for each atom on many, 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 many time steps until the run has lasted long enough so that you can start collecting statistics and start getting a feeling for how the system as a whole behaves. All right, so these forces are what we're going to talk about. We're not going to really talk about the simulations. That's another topic for another class, and a pretty complicated one too. So we just don't have time to deal with that kind of thing in this class, but we can talk about the intermolecular interactions. These guys, even if you're not doing explicit calculations like a simulation, they're useful for getting a qualitative feel for how things push on each other and interact with each other in a complex, condensed matter sort of situation. Also, when we talk about the Boltzmann distribution, probability calculations, just in the next topic, actually, a little bit anyway, then we'll need to be able to do some of these calculations to do those probability calculations. All right. There are bonding intermolecular interactions. There are non-bonding molecular interactions. The bonding ones are what they sound like. The two atoms are bonded to each other. If you start pulling on the two atoms and pulling them apart, the bond will resist pulling them apart. If you try pushing them together, the bond will also resist pushing them together. And there's energies involved with the forces and resistances caused by that single bond. If you've got three atoms bonded in a row like this, then there's a bond angle between those three atoms. And also, if I push on this atom and that atom, try to bend the bond, there are forces that will resist that bending, and likewise, if I try to open the bond a little bit, or open that angle a little bit, then there'll be forces that resist that. So there's two center, three center, and also four center bonding arrangements. Those are called dihedral angles, where you've got four atoms in a row, and the rotation then around the bond in the middle of those four atoms rotates this end of the four atom set relative to this end of the 4-atom set. And there will be forces that resist that rotation as well. And so we'll talk about all those cases. Then there's the non-bonding interactions. These are interactions that don't depend on actual chemical bonding. They're called through-space interactions sometimes. And there's a variety of those. We'll talk about each of them. Induced dipole, induced dipole. These are very weak, but also very, very common. So they actually have a great big effect despite their weakness. Interactions between charges on the molecules. Dipole-dipole interactions. Actually, we're not going to talk about that here. We're going to talk about, no, we're not going to talk about that here, though, because they're really kind of part of the charge-charge interaction. At least that's the way they're treated in simulations like this. And then there's H bonding. So let's strike that out. I put that before I even thought about what I was doing. It's such a common thing to put that I shouldn't have put it there. All right. So bond stretching then, the bonding interactions. If I have two atoms that are bonded to each other, let's say a diatomic molecule, or two carbon atoms in a carbon chain or something like that, any two atoms, and I start pulling or pushing, so I start here where the bond is at equilibrium, and I start pushing in this direction, or I start pulling in this direction, then of course forces will act to, if I start pushing, to try to resist my pushing, and in this case if I start pulling, forces will try to resist my pulling. And that's represented by a bonding potential, which has a curve like this. What this is saying is the energy goes up. If I'm here already, if I'm at the equilibrium bond length, the minimum in the potential, then if I try to crush them together, the energy goes up. If I try to pull them apart, the energy goes up. And that particular shape can be represented in a, well, it comes from quantum mechanics ultimately, but it can be represented approximately by a variety of different functions. One of the most common and popular one is something called the Morse potential, and that's this function here. Here's the energy of the bond. It's given by this function, which has three different parameters, D and A and R0, and those parameters represent these aspects or properties of the curve. D is the depth of the well. If you go out to here to infinity, that sets, you know, the level of when the atoms are far apart, and D is how deep the well gets, how strong the bond is, basically, as you come in and finally reach the minimum in the bonding potential. The quantity R0 represents the equilibrium bond length, the length at which the bond is most stable and most happy. And then there's this quantity A, which is a little bit more difficult to see what it's doing. It's basically saying how wide or how narrow this potential is for a small value of A, for example. It'll be very wide and broad. For a large value of A, it'll be very sharp and narrow. So A controls the scale or shape of the bond. The Morse potential is useful for a lot of things. I can't remember if we do many calculations. It's not probably the thing we do the most calculations with. One of the things you can do, though, is use it to get at the force constant or the shape of the potential right near basically it's the stiffness of the bond, shape of the potential right near the minimum. And that can be done in the following way. First of all, the forces acting on, in general, this is a general relationship that's good to remember if you don't know it already. The forces acting on the bonds, on the atoms, are equal to minus the derivative of the potential with respect to r. So if you take this function up here, take the derivative of that with respect to r, which is all this is over here, then you'll get the forces that are acting on the atom. And here's what you get when you take that derivative. I say here, notice that if I set r equal to r0, then this is 0 right here. That means we've got e to the 0. E to the 0 is 1 minus a 1, which gives this whole thing, makes this whole thing a 0. So you get no force when r is at the equilibrium bond length, which means that's the equilibrium bond length, right? That's the definition. That's where the bond is, that's where the bond wants to be. All right, but let's suppose we're right near the equilibrium bond length. Then right in that vicinity, the potential is approximately equal to a quadratic function like this. And the thing that controls how steep or how broad that quadratic function is is the force constant here, or spring constant. And that turns out to be related to the potential up here also. It's the second derivative of the potential. So take two derivatives with respect to r, and then evaluate whatever you get at the point where r is equal to r0. That's the value of the force constant, and it controls how stiff a bond is. The thing with a big force constant is a stiff bond, and usually a strong one too. And something with a small force constant is a soft bond, and usually a weak one also. Weak bonds tend to be soft. Strong bonds tend to be weak. Tend to be stiff. All right, the same kind of thing. So this is really, in many ways, the more useful formula. This quadrat or this harmonic. It's called a harmonic potential. Even more so than the Morse potential. There's a similar thing if you try to bend the bonds. And in this case, you get another harmonic function, but its variable isn't r anymore. It's now the bond angle itself. And there's an equilibrium bond angle, theta 0, and also a force constant for this. The force constant tells you how stiff things are. The equilibrium bond angle tells you what angle the bond wants to be at, the atoms want to be at. Theta 0 is the preferred angle for this set of three atoms. And like before, you can find this force constant by taking a second derivative of the potential with respect to theta and evaluating it at the equilibrium bond distance. Then finally, the fourth case is this four-atom case, the dihedral case. It's a little bit more complicated. First of all, let's define a plane that contains these three atoms, the first three atoms coming from the left. And let's rotate this bond until the fourth atom is also in that plane. That defines the zero angle for this angle around the bond that's called chi. That's a Greek chi letter. And now I rotate the fourth atom out of that plane, and the angle in general is between this plane and the plane made up by these three atoms, the last three atoms rather than the first three. And that's the definition of the chi angle. If chi is equal to 0, therefore, you have an arrangement of the four atoms that's like this. If you were to look down the end of it, what you'd see is something like this. There's other atoms out here, right, that we're not drawing, the ones that are, if it's a tetrahedral carbon chain, for example, then there'll be four atoms bonded to this atom right here, and so there'll be two more down here. Then you'll get an arrangement that looks like this. It's an eclipsed arrangement. This is this carbon atom, let's say, and then there's a carbon atom behind it. That's this one. And then these guys are these other atoms lined up right with each other. That's a high energy arrangement, unfavorable arrangement, because these guys clash with each other, bump into each other a little bit. The way I've drawn them here is little small circles. Doesn't look like they bump into each other, but they're really big. It really looks more like this. And they do bump into each other. On the other hand, if chi is equal to 180 degrees, that's this plane rotated all the way 180 degrees, then you've got this staggered arrangement, which is the low energy configuration, where all the atoms are in between each other and have the minimum amount of clash or bumping into each other. All of this can be described by still another potential function, which I've called U dihedral here. It has three different parameters. One is another thing that's at least written with the same symbol as a force constant, and I guess we can call it a force constant for lack of a better term. But it's really the height of the potential here. Another one is this quantity n. That's a multiplicity factor. I'll point out what that is down here. And then this quantity delta, which is a phase shift factor, that's usually set to 0, and n is usually set to 3. Here's what that function, notice there's a cosine in here, and it's a cosine as a function of chi, which means that it's a cosine as we're rotating around this bond from originally 0 all the way around 360 degrees. And so that's what we're doing here. We're rotating from 0 to 360 and looking at the energy of the system as we do so. When we're at 0, we're in this eclipsed configuration. The pendant groups are clashing with each other, so you're at high energy. When you're at 60, we've rotated off by 60 degrees, you're in one of the staggered configurations, and you're at low energy, so we're at a minimum. Rotate another 60, though, and suddenly you're in another eclipsed configuration, and so on. The system alternates between eclipsed and staggered configurations as you rotate all the way around. Eventually, you return back to where you were after a rotation of 360 degrees, and that's again one of the eclipsed configurations. Okay, that's the bonding arrangements. That's the bonding interactions. What about non-bonding interactions? Well, we've seen that there's a bunch of those. The first one is one of the more important. It's one of the weaker ones. It's one of the more subtle ones to explain. And it's also one of the more important ones. So weak and subtle and important. The reason it's important is because every single atom has this kind of interaction. It's called a van der Waals interaction. Let me write it all out. Van der Waals, which I think is a name probably everybody here knows. It's also called the Lennard-Jones interaction. We'll talk about that below. It's sometimes called a London interaction or dispersion interaction. This same kind of interaction, or very much the same kind of interaction anyway. I mean, all these names actually mean things that are slightly different from each other, but they're very similar. So they all, for our purposes, they're all the same. Van der Waals, London, dispersion, or Lennard-Jones, all these things are describing this effect. Let's suppose you have an atom. It's got a nucleus, which is positively charged. It's got electrons flying around it in orbitals, which are all negatively charged. If you apply an electric field to that atom, the electric field pushes on the nucleus, pushes it this way, and pulls on the electrons, pulls it the opposite way, and the net result is that you get a slightly positive end of the atom and a slightly negative end of the atom. And that's a dipole moment. It creates a dipole moment. And because it's not there all the time, if you take the electric field away again, the dipole moment disappears. It's called an induced dipole. It's induced by the presence of the electric field. Atoms that, well, virtually all atoms and molecules have this property that they can have a dipole induced in them, and therefore they're what's called polarizable. A dipole can be caused in them by exerting an electric field, or by a whole bunch of other effects too, for that matter. Once you've got a dipole on the molecule, the dipole creates its own electric field, and it looks something like this. This is kind of ugly drawing, but there's all this sort of flow lines of electric field going around the dipole. And that electric field can then come and act on another nearby atom and induce a dipole in it. And that means that if the dipole appears just by random chance, these atoms, after all, are fluctuating all the time. The electrons in the electron cloud around the nucleus aren't sitting still. They're all fluctuating all the time. The nucleus is moving around too. So there are going to be momentary dipole moments produced in the molecule, even if it's just sitting by itself with no electric field applied. It gets its own momentary dipoles. And those dipoles will create electric fields, which will then cause a dipole in a nearby atom. And because of that cause and effect relationship, there's a statistical tendency when atoms are nearby each other like this, for the dipole that happens to sit on one atom to be correlated in an attractive arrangement with the dipole that's on the nearby atom. So if you find an atom with a dipole moment that's pointing in this direction, you're more likely than random chance to find the other dipole in the nearby atom pointing in a way that's a favorable interaction. So you can see this is favorable, right? Because a dipole is a plus sign and a minus sign here close together. And if this guy is pointing this way, then that's a plus sign and a minus sign this way. And that arrangement puts the pluses and minuses near each other, which is favorable. So this is a favorable arrangement of dipoles. This one's also a favorable arrangement of dipoles and also the kind of arrangement that you'll find due to this what's called induced dipole interaction. This kind of interaction has a potential energy of interaction that's attractive and proportional to the distance to the 1 over the distance to the between the atoms to the 6th power. It's very strong. It varies very rapidly. As the atoms start to approach each other, this 1 over r to the 6th becomes a very strong interaction. On the other hand, the prefactor that's out here, so there's a constant that's out here, also is very small. And so the overall interaction is usually small, but every single atom and molecule has it. And so the collection of all these interactions ends up being important anyway. If you take any two atoms and look at them, there is this dipole-dipole 1 over r to the 6th interaction attracting them to each other. But if they get too close, there's also a hardcore repulsion. That turns out to be at least approximately 1 over r to the 12th power. And if you combine those two, the 1 over r to the 6th term and a 1 over r to the 12th term, then you get what's called the Lennard-Jones potential. Here it is. This is the Lennard-Jones or induced dipole, or London, or dispersion formula. This is actually called the Lennard-Jones potential, and it's got a 1 over r to the 12th term and also a 1 over r to the 6th term with a minus sign here. So this is the attractive part. This is the repulsive part. And if you plot this energy versus the distance between molecules, like here, it looks a lot like the bonding potential, though it's much weaker, and it's not the bonding. It has a different origin, physical origin, than the bonding potential. But it's got largely the same shape, actually. It's got a minimum. It tapers off to 0 as the two atoms are pulled farther and farther apart, and if you try to crush them together, there's a repulsive term that goes, well, very high, if not to actually infinity. There are two different parameters that control this function. One is this epsilon ij. The other one is this r min ij, which appears in two places here. Those are the two parameters, and r min ij is the same thing as r0 in our earlier examples. It's the position of the minimum in the potential, and epsilon ij is the depth or the size of the stickiness of the potential. All right, I've already said this several times, so I won't belabor it now. These are weak interactions, but every atom has them, so they add up, yes. And they're responsible for a lot of phase behavior, especially. They're also responsible for a whole lot of other behavior. Pretty much everything where atoms start, and maybe not in the gas phase, but in any liquid or solid phase, van der Waals interactions are playing some kind of important role. All right, that's van der Waals interactions. The next thing is charge-charge interactions. This is called the Coulomb potential. It comes from physics, it comes from electrodynamics, or electrostatics, really. And it's a very standard, absolutely bread and butter kind of interaction between any two charged groups. So if I've got a distance between two charges, and the two charges are q on one atom and q on the other one, qi and qj, then the energy of interaction between those two depends on how far apart they are and what their charges are. And then there's all these constants out in front, and I give the value of those constants. The only thing that's really important in those constants is this thing called the dielectric constant, and we'll talk a little bit more about that further down. If I plug in, this is usually in inconvenient units. It's in electrostatic units that nobody probably in this class is familiar with, and which are confusing because there's several different types of electrostatic systems of electrostatic units, and you can easily get confused about which system you're in. In fact, it takes some expertise to really know how to deal with those units. And so I boiled it down for you. Here is the formula in nice units. So there's this big thing in front, this big number in front, 1391. That has units of kilojoules per mole, actually, times angstroms divided by electrons squared. And now, rather than these charges being in Coulomb units, which, what's that? they're now in electron units, right? Which means that it's +1 for a sodium atom, it's -1 for a chloride ion, it's -1 for an electron. It's the units that chemists normally use for charges on things. The distance between the atoms has been set up to be in angstrom units. That's convenient. And all these other constants, I put the actual numbers in there and boiled them up into this one big constant, 1391. And that gives you out an energy in kilojoules per mole, which is the one we're mostly familiar with. So this is the more, well, much easier formula to use. The only thing that's left then to talk about is this dielectric constant. The dielectric constant represents the fact that if I have a charge here and a charge here, and now I have a polarizable medium in between, so I've got something like water in here, then all the dipoles in this water will arrange themselves so as to partially cancel. So the negative tips of the dipoles in the water molecules will arrange themselves so as to partially cancel this positive charge. And they'll do the same thing over here, but in the opposite direction. All the positive ends of the water molecules will arrange themselves so as to partially cancel that minus charge. And the net effect, the mathematics is kind of tricky and it's not obvious, but the net effect is just to make the interaction a lot weaker. That doesn't change the shape of the potential or anything. It just makes it weaker, just divides it by a constant. And the constant is 80 for water, so that means the interaction energy between two charges is 80 times weaker in water than it would be in vacuum, right? If you're in air or vacuum, that epsilon here is a 1. So that's the strong case. That's the case where the interactions are strongest. If you're in water, it's 80, so that means it's 80 times weaker than it would otherwise be. If you're in the middle of a protein, it's about 4. It varies depending on where you are exactly in the protein. It's not really a constant in that case. And if you're in lipid, it's about 2 and so on. So that's the range of things. Most of the time, it's not so huge, but in water it really is, because water is very polar. The more polar the environment is, the bigger the dielectric constant is. All right, so I say some of the same things down here. The charge-charge interaction is very strong in vacuum. If we use our nice formula here, and suppose I have a +1 charge interacting with a -1 charge at a distance of 10 angstroms, pretty far apart, much further apart than a single bond length, for example, 4 times bigger than a single bond length. Then the charge on one, Z1 is 1, Z for the other one is -1. The dielectric constant is 1 if we're in vacuum. And the distance Rij is 10, and that gives you an energy of interaction between these two, a favorable energy of interaction. Actually, I forgot something here. There should be a minus sign there, right, from that minus sign. A favorable, a negative number, and therefore a favorable energy of interaction, which is on the same order as a chemical bond. It's almost as strong. I mean, this is a little bit weak for a chemical bond, but there are chemical bonds that are in that range. And most of them aren't a whole lot bigger than that. So interactions in vacuum, charge-charge interactions in vacuum are very strong. On the other hand, if you put them in water, same calculation, but now with a dielectric constant for water underneath there, now it's only 1.7 kilojoules per mole. That's pretty weak. That's starting to get on the order of thermal fluctuations. This is weak enough so that these two guys won't be able to stick together very much of the time. Thermal fluctuations and vibrations and collisions and stuff will drive them apart. Whereas this is way strong enough for them to stay absolutely stuck to each other. All right. If you put it in ionic solution, then you get what's called counter-ion screening, and I think we'll talk about a little bit about this next time. I don't want to go into it right now because it'll take too much time. But basically, if you've got a plus charge, then there are negative counter-ions in solution. This is a sodium ion, then there'll be chloride ions in solution, for example, and they tend to congregate, they tend to hang out near the plus charge, which means that if you're out here trying to see what's inside, you're looking through a screen of negative charge to see that plus charge. And basically these negative charges largely cancel this plus charge. So what this guy out here actually sees is a very small remnant of the full positive charge. And the same is true for a negative charge. There are positive counterions that screen that. And so in ionic solution, electrostatic interactions are largely screened. They're much, much, much weaker. I mean, they're much weaker already just due to the water dielectric constant. They're even much weaker yet because of screening. And so electrostatic interactions are still important for more subtle reasons, but they get largely canceled in an ionic solution, a water ionic solution. All right, last thing I want to talk about before we end this lecture is a little bit about one other kind of important intermolecular interaction, that's hydrogen bonding. Everybody here is familiar with this, I'm sure. If I have a highly electronegative atom like oxygen with a hydrogen attached to it, or nitrogen or fluorine, and then I have that hydrogen nearby, let me change this color here, nearby another electronegative atom like oxygen or nitrogen or fluorine, then they can form what's called a hydrogen bond. Hydrogen bonds are pretty strong, 20 kilojoules per mole. So a chemical bond is hundreds of kilojoules per mole, so this is quite a bit smaller than a chemical bond, but it's still very significant. And they tend to be quite a bit longer than typical chemical bonds also. Chemical bonds tend to be between about 1 angstrom and about 3 angstroms. Hydrogen bonds tend to be between about 2.5 angstroms and 3.5 angstroms. So they're longer anyway. They're not enormously long, but they are longer. Also, unlike chemical bonds, which generally, you can't get more than a certain fixed number of them, hydrogen bonds are okay if you've got a whole bunch of, this is called the donor over here, right? And this is the acceptor. Whole bunch of donors bonding to the same acceptor, that's okay for hydrogen bonds. And also the angle at which the hydrogen bonds get made. So this angle here, here's a straight one, here's slightly bent ones. That's also not so important. There's quite a wide range of angles like that are still good hydrogen bonds. However, if they get if the angle gets too sharp, then yeah, not so good anymore. Yeah, also possible is for a single acceptor to hydrogen bond to, a single donor to hydrogen bond to several acceptors, or vice versa, several donors hydrogen bonding to a single acceptor. All those things are possible. All right, and that's nearly the end. I just wanted to make one more comment, which I think isn't really part of this class, but is important for understanding biophysical chemistry generally, and this is really kind of a biophysical chemistry class. So, and that's to say that in lots of sort of lower division classes, there's a tendency to focus on hydrogen bonds, especially in protein and especially in DNA. And and it's right to focus on those things because they do play an important role. But the role they play is in determining the structure of the protein, the way the protein folds up, for example, or the base pairing structure in a DNA. But the hydrogen bonds aren't really holding the molecule together. It kind of looks like they are, right? If I have an alpha helix here, and I've got hydrogen bonds going between pairs of donors and acceptors along the length of the alpha helix, you might say to yourself, well, those hydrogen bonds are holding this alpha helix together, and that isn't quite right, and here's why. It's because if you unfold that, the hydrogen bonds get broken as you're unfolding, but they immediately can form hydrogen bonds with the surrounding water, right? The water itself is all hydrogen bonded up and is a hydrogen bonding solvent. And so the hydrogen bonds don't really get broken. They just get replaced. Instead of hydrogen bonds between units and within the molecule, it's hydrogen bonds between something on the molecule and the water surrounding it. And so the net energy change due to the breaking of the hydrogen bonds usually isn't very big. Mostly the hydrogen bonds get replaced. The role the hydrogen bonds play is in making this shape be the favored one as opposed to some other folded up shape. And the same with the DNA. It's the hydrogen bonds in the DNA, of course, if I crudely draw, an A and a T this way, then you've got 2 hydrogen bonds, or a G and a C, bases, 3 hydrogen bonds. Those hydrogen bonds determine the base pairing, and that's really important biologically. But they aren't holding the DNA molecule together. The DNA molecule once it comes apart, all those hydrogen bonds get replaced by hydrogen bonds with the water. All right, and I think that's it for now, and so we'll stop for next time.